Okay, this is our third session. We're going to be looking at 4 quick steel bridge case studies. We have 4 different speakers today. So you're going to get a view of these 4 case studies, but if you need more information, I encourage you to go to the shortspansteelbridges.org website where you can find more information on these case studies and other case studies. Again, we encourage you to ask questions or make comments in the chat. We encourage you to respond to other people's chats, or you can use the Q&A button. That also works, and we will try to answer those along the ways. The ones we cannot, we will save for the end, and Dan Snyder, the director of the Short Span Alliance, will coordinate those towards the last of or after the 4 presentations. And with that, I'm going to also ask again, just like the previous 2, that the speakers introduce themselves so that we save time. And with that, we are going to go ahead and start with Mark.
Good morning. I am Mark Story. Just a second, I'm sharing my screen real quick. And I am with Whitman County, Washington. For those of you that don't know that, we're just south of Spokane in eastern Washington, right along the Idaho border. So I'm going to talk a little bit about the Belmont Bridge replacement project, Whitman County. We built this last year. The Belmont Bridge was a replacement project for a 1921 all-wood structure. It was 19 feet long and 22 feet wide. The original wood structure was built in 2000. Was rebuilt, in 2002 on original wood piles with wood back walls. The bridge was experiencing lots of deterioration and lots of flooding going on. This bridge had actually been overtopped a couple of times since I've been at the county. The replacement bridge, as with many in Whitman County, was planned, I'm sorry, I didn't even advance the slides, was planned to have a longer span in order to improve the hydraulic opening of the bridge. This also makes it easier to build new foundations behind the existing wood pile foundations. The channel, Kelly Creek, has an average mean channel width of about 20 feet, and the road approach on both sides of the channel is normal to the channel alignment. Therefore, neither the existing bridge nor the replacement required any skew. That made it fairly simple. One of the goals of the replacement bridge was to open up the channel wider than it was and raise the bottom chord of the bridge to get it above the 100-year floodplain. Whitman County has a dedicated bridge crew of 5 people and has the equipment and experience to replace small bridges with county forces. We've been doing this for many years. Until recently, the county has traditionally constructed concrete superstructure bridges and then only recently switched over to steel superstructures for much of what we do. The county builds the foundations and all the site work and contracts for the casting and the delivery of the pre-stressed concrete, or in this case, the manufacturer of the steel girder superstructure. For the Belmont Bridge, we competitively bid the manufacture of both the steel and the concrete. The successful bidder and the lowest cost was True North Steel with a steel rolled beam steel structure. True North Steel was out of Missoula, Montana. Another nice thing to note is that when we bid these out, we asked for the manufacturer to actually produce the shop drawings and stamp them. So here's a couple of pictures of us taking down the old bridge. Basically, when we moved the old structure, the county forces tries to isolate the area of the construction and make sure that we're not dropping a lot in the creek. It's impossible to do that perfectly, but there's a lot of real requirements on that by Washington Fish and Wildlife. So we do our best to isolate the site. So Whitman County has been building bridges using county forces for several decades. County forces are capable of building bridges up to about 60 feet in length. This is a practical limitation just because of the time available. The same people that build bridges also maintain our bridges. We have over 300 bridges to maintain, so it's a big time commitment. Typical earth materials consist of soft, firm silt and clay alluvial soils overlying basalt bedrock. The alluvium is not typically suitable for support of the structures, particularly when considering scour potential. Therefore, most of our bridges we support using H-piles driven into the basalt bedrock underneath. The depth of the basalt is usually between 5 and about 30 feet, although we've had a couple of them show up at about 70 feet, which surprises us a bit. We found that it's a lot cheaper and simpler to just simply drive steel piles to bedrock and then build tieback anchors as mitigation if the final bearing depth is not below the scour areas. About 10 years ago, the county upgraded to a hydraulic pile driver that is mounted to a large trackhoe to install the piles. You see the picture of it sitting right there doing this Belmont Bridge. The number of piles is determined based on the anticipated loading and the length of the bridge. Sorry, I have to use my paper because my screen is doing weird things. For the abutment pile cap, rather than forming and casting concrete and waiting for it to cure, the county installs a top plate or a pile cap using the same size H pile that we use to drive the piles. You see pictures of it there. Then we use steel back wall installed behind that to put the backfill up against, and then we compact structural fill behind that. This is a picture of basically the final product just prior to putting the bridge on it. By making the bridge longer than it once was, or in the old bridge, in fact, I'll go back just a little bit, and you'll see right there, we're driving piles behind, right behind where the old abutment was. It makes it very simple for both safety on the job site and for construction. This simplifies all the requirements from Washington Fish and Wildlife as well. So it's really simple when we can isolate ourselves as much of the stream as possible. After the piles and the pile cap are completed, the old foundations can then be removed with less disturbance to the channel, and then riprap is installed. So the final dimension of the superstructure on this project was 32 feet long by 28 feet wide. So the bottom of the new bridge needed to be raised above the creek further than the original wood bridge. So the road was raised about 2 feet to accommodate the new superstructure. The modular rolled beam steel bridge consisted of 3 modules that could be shipped to the site on 1 truck rather than 3 trucks as we used to do with the old concrete bridges. Selecting a bridge structure that can easily be handled by 1 or 2 excavators significantly reduces the overall project costs and shortens the construction times. You can see here we're able to use a large loader in the trackhoe to basically put these modules into place. They're lightweight enough to do that with county forces and county equipment. Each module had 2 or 3 weathering steel rolled beam girders fully assembled and a corrugated steel deck and side dams attached. Now this is easy for placement of gravel riding surface. You'll note in the picture on the right, you'll see a steel beam or a steel rod right on top of the corrugated deck, and that's basically grader rails for when we put gravel over it later on. Here's a couple of pictures, and there's a great picture in here. If you look in the upper right, there's Dr. Barker actually working on our crew. We decided not to rehire him this year though, but just to prove that he does know how to use a pry bar. So here's some pictures of the 2 girder superstructure modules being erected. The modules are shipped to the site and assembled with the side dams, simple cross frame diaphragms, and the guardrail stubs, as you can see on that left photo. There's no concrete curing time, so we can put the bridge into service rather quickly after this. So here's just a couple of nice pictures of the bridge sitting on top of the foundations. You can already see the restraining anchors put in place on the left, and then on the right, you can see the fully installed modular pieces before we put any gravel or do any backfill to it. We did have to fix that sort of right corner that you can see in there. We had to put some gabions in there to retain the soil. Here's the next picture, adding the fill to the bridge. This was on a gravel road, and so you can see the gravel goes right across the deck. And this is prior to installing the guardrail on there. And you can see the soil spilling off to the right. So it gives you a sense for how easy that was to put together once we had all the pieces in. In addition to the direct cost, there's always indirect costs associated with the bridges. With their different superstructures. With a concrete superstructure option, Whitman County would have to hire a crane service to lift the concrete girders into place. With the steel modules, we did not need to hire a crane service. Crane service in our area usually runs $4,000 to $8,000 per spot, and that's assuming good access. The steel girders can be lifted with the county forces, just getting rid of all of that. And it also helps quite a bit with scheduling, because I don't know how many of you work with crane services, but scheduling them can sometimes be a 1 or 2 week option just to get them into the right spots. So this Belmont Bridge, the total cost of this project was about $168,000. And the concrete superstructure alternative was $85,000. If you look at the cost estimate, right, or the cost breakdown, these are just rounded numbers. The steel superstructure was about $50,000 delivered to the site. The concrete superstructure alternative would have been about $85,000. So that alone was about a $35,000 increase had we gone with concrete. So we used to build exclusively with concrete. We believed it was a better product for a lot of years, and I think we have taken a little bit of time and rethought that a little bit. We now believe steel might be the better option for what we're doing, although any given or specific location you're going to want to look at individually to see what's the most applicable. So the Belmont Bridge was completed during the summer in accordance with our permit from Washington Fish and Wildlife. It took about 4 weeks to complete and then was open to traffic. There was a little delay in there for some internal issues, but the 4-week period was the total time building the project. The work included the installation of a temporary detour bridge, which is a single-lane steel bridge that was purchased about 8 years ago and used on all our construction projects for small bridges. The stream site isolation, erosion control measures, pile installation, pile cap installation, welding of the seismic anchor clips, the placement and completion of the superstructure, and all of the associated road building activities were all within that 4-week period. I think I already talked a little bit about that. We did a competitive bid on the structures, the superstructures, and that was the difference of $35,000. By the way, that's my bridge crew. They're just regular guys that know how to build things. So for a couple of quick takeaways, the steel bridge superstructure costs are competitive with other bridge materials. We found that to be very much true in the last couple of years. They can easily be constructed with county forces without specialized skills. They're lighter weight, resulting in economies in required construction equipment and substructure costs. Steel modular bridges allow for ease of erection, faster erection times, and the modules fit together great due to the quality of the shop fabrication. For long-term maintenance in this bridge especially, with the steel deck grader rails that allow for the gravel road surfacing to go clear across the bridge, which makes it far easier for us to maintain a gravel road like this. I don't know who else maintains gravel roads with bridges, but it's the maintenance crew always has a hard time when they come up against a concrete deck with a gravel approach. So anyway, that is my quick and dirty presentation. I don't know if there's time for any questions. I'll turn it back over to Michael.
Thank you, Mark. That was a great presentation. And yes, I was out there for the installation of the superstructure. And I agree, Mark has a very good bridge crew. That bridge went in more or less in 1 day. Took a little longer to put the gravel on, but the bridge went in 1 day. And we're going to go from Washington to Illinois. And Jeff Blue is going to talk about an innovative bridge design that he installed.
All right, good morning. Can you see my presentation
That
there?
looks perfect, Jeff.
All righty, awesome. Like Mr. Barker said, my name's Jeff Blue. I'm the county engineer in Champaign County, Illinois, which is 100 or so miles south of Chicago. So we're down in the farmland of the state of Illinois. Let me see if I can get this thing to advance. It's not wanting to advance. There we go. All right. So now it's advancing too far. Okay, so what I'm going to talk to you a little bit about, most of this is about press brake tub girders, but I want to kind of give you some insight as to how we got to thinking about the press brake tub girder here in Champaign County. So in Champaign County, you know, we go through a bridge selection process just like anybody else does. We try to look at the lowest cost and the best possible scenario we can make for our bridges. We have 600 bridges in Champaign County. A whole bunch of them are just little 50-foot structures over county ditches that basically drain the farm fields in Champaign County. So because we're so flat, we just have a whole bunch of these small drainage districts that go underneath our roadways. So we have to go ahead and put bridges in, obviously. So the first thing we used to look at was the precast concrete deck beam, which is kind of the typical use that we would always look at. It was typically used on our township roads with our lower volume traffic, and on some rehabilitated county roads where we had bridges where we had a precast, pre-stressed concrete deck beam in place, and we were going ahead and just replacing that. So these were typically placed in areas where we have less susceptibility to be exposed to chlorides, because most of our townships don't use salt. And the reason we did them because they're quick, and the cost, and these costs that I'm showing you today are pre-COVID costs. So we haven't really looked at our costs and tried to figure out everything post-COVID. It seems like everything's up 30 to 40%. But these the cost of these precast, pre-stressed concrete deck beams was about $200 a square foot in total cost. And this is all contractors. We don't do any kind of bridge construction like Mark Story's crew did. And we're also paying about $86 a square foot just for the beams. Another option that we like to use on our county roads are, rolled beam concrete deck bridges. These are typically built on our higher volume county roads. When I say higher volume, up to like 5,000 a day. We don't have any 40,000 ADT vehicle roads in our county. But we do weathering steel. These are on our roads that we salt. We have a bare pavement policy, and we'll go out and run when it's snowing 24/7 until we get all the roads squared away. So these things have seen a significant amount of chloride contamination. A little bit higher cost for these, you see there. Our pre-COVID costs were about $300 a square foot in total cost. Obviously, they take a little bit longer because you got to set the beams, you got to pour the deck, you got to do the whole 9 yards. So the construction is a bit more tedious than your typical precast deck beam bridge. We've also done some reinforced concrete slab bridges where, it's like an 8 or 10 inch reinforced concrete slab, no steel beams underneath them. We build these on our county or higher volume township roads where we don't want to have a growth in our roadway. And when I say that is what I mean. I don't want to have to go back 300 or 400 feet and regrade the roadway and repave it and do all that stuff because of the fact that we're putting steel beams or these thicker concrete beams on our roadways, which ends up making the road profile get higher. And then we have to rebuild the road going into it. So we spend some more money on the bridge, but we end up not having to spend as much money on the roadway. We don't have to buy right of way. We don't have to do those types of things that go with kind of having to expand the height of your bridge. These are higher cost. $500 a square foot is what we're seeing on these types of bridges here in Champaign County. Obviously, the construction is a bit more tedious because you got to form all that up and get it ready to pour. Other options that we've looked at in Champaign County, box culverts. We've done poured in place. We've done precast concrete box culverts. We've done the metal arch culverts, which is what you see there on the bottom right, where it kind of comes in as an erector set, and they unload it off the truck, and the contractor tears out the old structure and starts building this thing on site. Typically, they'll build it on site and then lift it and set it into the stream when it's pretty much ready to rock and roll. But we started talking about these short span bridges with the Short Span Steel Bridge Alliance back in 2019. Also, as the county engineer in Champaign County, right now I'm the president-elect for the National Association of County Engineers, NACE. And NACE has a really, really good relationship with the Short Span Steel Bridge Alliance. And we have a dinner prior to the annual NACE conference where the executive committee and the Short Span Steel Bridge Alliance folks get together, and we have a little cocktail hour, and we have a nice dinner, and we talk about what's going on, in the world of bridge building. And at the 2019 conference out in Kansas, they started talking about these press brake tub girders, and I said, well, sounds like something that I'd like to try in Champaign County, even though we haven't had any of these built in the state of Illinois. And probably as any other state association goes, the state of Illinois, when you start talking about new things, the bridge office at our Illinois Department of Transportation gets a little bit nervous. So I talked to them about wanting to do one of these press brake tub girders, and you'll see there kind of the general form of the press brake tub girder after it's been bent and ready to go at the plant before it's galvanized. So after I kind of got the thumbs up from IDOT to say, yeah, we'll go ahead and we'll give this thing a shot, I went back to the Short Span Steel Bridge Alliance and said, we need to form a team from your group of people that we can work with to try to get this thing going. So we formed a little group between Valmont Industries, SSAB of America to supply the steel, and McCann Concrete, which is a precaster here in Illinois, to do the precast top on them. And I said, so what's going to have to happen here is you guys, in order for this to be successful in the state of Illinois, you're going to have to be competitive with our precast pre-stressed deck beams, because that's the type of bridge that I foresee this kind of being used as a quick construction on a township road, pretty, simple construction type project. So I said, your costs are going to have to be very similar in order for you guys to kind of get into the market here in Illinois. So we actually did a purchase order with Valmont for the press brake tub girders, which included the tub girder, the concrete deck, the freight, the shop drawings, and the load rating. So the county purchased the material for the superstructure of the bridge, and then we went ahead and hired a contractor to kind of put it all together. And you'll see there that the material cost only were about $82 a square foot. If you remember back at one of my first slides on the precast pre-stressed deck beams, they're around $85 a square foot. Now that was delivered, but still they're in that same ballpark of where we're getting those concrete beams, which is where we needed to be. And you'll see the total cost of the bridge, including everything, was $263 a square foot, which is right in there and competitive with those precast pre-stressed deck beams. So the construction process for these is really simple. We got the tub girders, like I said, from Valmont. They were hot dipped galvanized. You can see a picture of them there. They were shipped down to our precaster in Illinois on a truck and set in their yard. You see the 4 tub girders sitting in their yard there. The precast decks were poured on top of the tub girders by McCann. You see our contractor there kind of giving a little inspection of what that precast deck on top of those tub girders looks like. So we had 4 of these that we needed in order to construct the township bridge that we did. And so the construction process in Illinois, and Mark talked about his process out west, is, at least in Champaign, Illinois, we hire a contractor, they drive the pilings, they pour the abutments, they put the riprap on the slopes, they prepare the stream, and basically then whatever is coming in that you're going to put on top, whether it's a rolled beam, a concrete beam, these press brake tub girders come in on trucks, and we got a crane on site that the contractor is supplying, and they're going to pick these things off the truck like you see here in this picture. They got big choker straps that go through the holes that are precast into the precast deck, and they pick them up off the truck. You see it there. You got the girder underneath and the concrete deck on top, and there's a concrete back wall that was also precast there. So everything is ready as soon as you put this thing on top of the abutment. And there they are, swinging it into place, putting it on top of the abutment. There's a sole plate that is attached to the beams as they come in, that sits on top of a pin that's in the abutments that pins the whole thing together. The only issue you have when we're setting these beams was that, see the rebar coming out there in that closure pour. They had to do a little finagling of that because they would come in contact with each other, and so you had to make sure you bent them just a little bit here or there to make sure that they weren't conflicting with each other. The beams were all set in one day. Like I said, we only had 4 beams. It took an hour or so to set each beam in place. So it was a real simple process to set these beams. And then, like I said, they're pinned in place, and there's an 8-inch closure pour. You see that area in between the beams where we got on our concrete beams, we'll put a grout material in there. But in this, if we got an 8-inch closure pour, we use some pretty high strength stuff between the beams. You can see them kind of troweling off that closure pour there. The material that we use was this transpo, which was a polymer concrete. You can also use ultra high performance concrete in that closure pour as well. We chose Transpo because of the ease of its construction. They basically mixed it on site, put it in a wheelbarrow, took it over to the 8-inch closure pour, poured it into the void, and troweled it off with a regular trowel. The crazy thing about this stuff is we did some testing of it 24 hours after it was put in place, and it was 9,000 PSI material. That's some pretty high strength material there that you get in 24 hours. So there's a little look at what it looks like underneath the bridge with the grouted riprap, the abutment, the press brake tub girders with the beams on top. We chose a Midwest guardrail system to put on that because for ease of construction. I'm sure there's all kinds of different guardrail systems you can put in with these precast concrete decks on top of the press brake tub girders. Bare deck, Mark talked about having to maintain a gravel road with a bridge. This actually is a seal coat road. So the approaches coming in and out of it are seal coat, and the road is seal coat. You see a new seal coat there. When we do our precast deck beams, no matter if they're on top of a press brake tub girder or any kind of concrete topping on anything in Champaign County, we've chose to use the Pavex material as our concrete sealer. And these beams were actually sealed at the plant right when they were put on top of the press brake tub girders. They went ahead and sprayed them with this Pavex material to get them good and sealed up. So when they got delivered to the site, they're ready to set. We don't have to worry about putting any kind of sealer on this deck again, except for possibly along the closure pour, but that stuff is rock solid anyway. So here's a look at your most long-term bang for your buck for these type of projects. You see the precast beams were $200 a square foot, 50-year life. The steel beams with the concrete deck were $300 a square foot. We expect about 75 years. Now, these aren't taken from anything except my own experience, these numbers expected life. I didn't go and do any kind of research on these, but this is what we expect to get out of them. On a concrete slab bridge, 75 years, and on the galvanized press brake tub girder with the concrete deck, we're hoping to get 100 years. So you can see the cost and how they relate to how long these things are going to last. So I really think the press brake tub girder, regardless of whether you're going to put a precast slab on top of it or whether you're going to pour a deck on top of it, if you get that thing galvanized and get it set in place, you're going to have a bridge that's going to last a long time. And in Champaign County, as I'm sure in a lot of counties and other small entities across the United States, it's pretty much up to the county engineer to choose the type of construction, and we take that information to our county board. We get it approved by them. They don't worry about whether it's going to be concrete or steel. That's my job, not theirs. So I just tell them, hey, trust me, I'm a bridge engineer. And then if they don't like that answer, I say never, but never question the judgment of the engineer. So I thank you all for viewing. Go Illini. We're here in the home of the University of Illinois. So thanks a lot for having me.
Thanks, Jeff. That is a great presentation, especially the comprehensiveness of all the different kinds of bridges. So we're going to go next door to Missouri, but I do have a question for you, Jeff. This was the first time you built one of these press brake tub girders. Do you expect the premiums that some of your contractors and suppliers charge because it was the first time will go down to where that press brake may even become more economical?
I hope so. I mean, we actually thought about that pre-construction, and we had the contractors who were likely to bid on this project come in for a pre-bid meeting, and we had a representative from Valmont come and just talk about how these things go together. But
oh, we lost the audio on Jeff. He might have locked up a little bit.
But I think there was still some apprehension on behalf. But I can tell you the contract.
Okay, we're going to move on. Jeff, you're cutting out. Jeff, if you can hear me.
Who bid this way in a like that.
All right. Thank you, Jeff. You're cutting out. But
sorry about that. Thank you.
That's okay. There's a couple of questions in the Q&A if you don't mind going there and looking at that. And with that, we're going to go next door from Illinois to Missouri with Joel Ham with a very handsome bridge option?
Thanks, Dr. Barker, and thanks everyone for tuning in. My name is Joel Hom. I'm a senior engineer with Contech Engineered Services. My duties primarily is working with our bridge consultants, helping to develop buried bridge projects. That process often also involves interacting directly with various agencies, engineers, and contractors during different parts of a project. We can get involved at any point from the beginning stages of conceiving a project to looking at alternative solutions and even value engineering. And then even during construction, I'll sometimes get involved with questions or issues that come up there. I'm also involved with various ASTM, ASHTO, TRB, Short Span Steel Bridge Alliance, and other organizations on development and improvement of various standards relating to buried bridges. Oftentimes reviewing research papers and providing some input, and also educational training opportunities, either through our bridge consultants or through some of these different agencies. I'm also the current chair of the TRB AKB 70 subcommittee on buried bridges, which covers all types of buried bridges. I'm a licensed professional engineer in 27 states and reside in Hastings, Minnesota with my wife and between 1 and 5 children, depending on the time of year and who's in school or visiting or whatever. So I'm going to talk about this project in Lawrence County, Missouri. This was a DOT project, but certainly everything that we did on here is applicable for more public works type projects and different types of settings. But it's a pretty good example of something that's becoming a little bit more common. This project was part of a larger Missouri DOT design build project that involved the replacement of 19 bridges over a 29-mile stretch of I-44 between Joplin and Springfield, Missouri. The Route 96 and County Road 1147 projects involved replacing 4 of those bridges with a single buried bridge at each location. This project was developed through the design build process, with the design build team consisting of Emery Sapp and Sons as the contractor and a partnership of the Lockmuller Group and Parsons Engineering as the engineer. So the design build process it's a pretty collaborative process, and with a lot of back and forth with the design team to find the best solution as we go. It's a very effective approach for developing buried bridge projects because we can get real-time input from the engineer on how the structure meets the project requirements, while getting input from the contractor on how design decisions affect overall costs. In terms of getting the bang for your buck, that's really the optimum approach to take. A lot of agencies and a lot of states don't really have that as an option. The next best thing to that would be maybe working on a performance specification, which allows that type of flexibility to happen somewhat during the bidding process, so that you can really get dialed in on what you're doing. On this project, efficiency was the goal, was the primary goal, speed of construction and minimizing traffic disruption. There's a lot of traffic on this roadway, and one of the things they want to do is avoid road closures and things like that. And also cost ended up being a factor, the initial cost as well as long-term costs. They started looking at concrete girders and other types of traditional, even rolled girder type of bridges. But in the end, buried bridges ended up being the best option. The primary reasons there was the speed of construction. Really, all buried bridge projects are accelerated construction projects. We had the ability to, and a lot of flexibility to do stage construction and eliminate any kind of a detour. And then also along with that, there was much lower long-term maintenance costs. These structures at the road level, the maintenance consists of maintaining the pavement. Whereas with any other type of bridge, you're talking about bridge techs and joints and bearings and things like that. So that was a big selling point to the DOT with allowing this as a solution. And then there was also a lower initial cost compared to all the other options. So this really checked checked all the boxes they needed to be checked at each type of consideration. So that this illustrates part of the process of finding the best geometries. The Route 96 structure on the left here needed to be a box geometry because it had to be sized to fit around a certain clearance box for the traffic going through it. And then we were also limited by the existing bridge structure. I guess I didn't mention before that both of these were constructed underneath the existing bridges while they were in service. So these are fully assembled without taking traffic off the existing bridges at all. So with that being the case, that really drove the geometry for both of these. So there weren't a lot of options with the Route 96 structure. With the County Road 1147 structure, there's a lot more height to work with. So we could look at different arch shapes and box shapes. The main differences there are that AASHTO has different backfill zone requirement limitations for boxes compared to arches. So the arch shape is going to be a more efficient shape, but it requires a wider backfill zone, while the box doesn't have quite as wide of a zone, but it's got a less efficient shape, so that might be a thicker steel gauge. So during that process, we're evaluating, does it make more sense to spend a little bit more on the structure and less on the backfill, or the other way around? This process, these are all designed and developed using finite element analysis, so this process is pretty easy to do. When you hear about custom geometries, a lot of times that people envision that means it costs more. In this case, it's the opposite. Doing custom geometries on these types of projects always saves money. So these are the final geometries we ended up with. The Route 96 structure on the left, we had a box culvert structure that was about a 40.5-foot span, fit around the clearance box and fit underneath the bridge. And then the County Road 1147 structure ended up being a dual radius arch structure. Both of these were set on stem walls, in part to better accommodate drainage through the structures. There were some drainage ditches that they had outside the roadway. And this also raises it a little bit to avoid or to simplify maintenance and cleaning with regard to some of the de-icing salts that would accumulate over the winter months. So this is a view of the Route 96 structure. Route 96 was an entrance ramp onto I-44. It passed underneath both bridges at a skewed angle. So one thing that's common with these structures is each individual ring is either 30 inches or 45 inches wide, and the design really works if the ring is complete. If those rings are cut, then you're interrupting the flow of the forces, and a lot of times there's a need to, especially on a skew, you need to reinforce that. Usually with these size structures, it would usually be a concrete head wall. So there was a desire to not have to do that because it would slow down construction and add cost. So we ended up sort of creating a kind of a fake skew on the structure by using an unbalanced step bevel. So the step bevel, what we mean by the step bevel is you start at the crown of the structure, you step down a couple of feet, and then you just cut a bevel in some of the plates at maybe a 2-to-1 or 3-to-1 angle, and then there's usually a step at the end of that. And by doing that, you can accommodate fill slopes. So you can cut those at any angle to accommodate these fill slopes, and you don't have to do it on the other side. So in this case, they opted to do the unbalanced step bevel, saved a lot of cost and time associated with a concrete head wall. It made maintenance of the existing grade slopes easier. They could just do what they were normally doing for mowing on those slopes. And that also gave them the flexibility to expand these in the future if needed. All you have to do is take off that bevel and you can continue building on more structure if there's a need to widen lanes in the future. The County Road 1147 structure was more square with the roadway. So in that case, we just did a straight step bevel with the bevels on both sides. They were able to maintain the same fill slopes that they had on the rest of the highway. So from a maintenance standpoint, nothing really had to change there. So both of these, I mentioned before, both of these structures were assembled with the existing bridges in place. The way that normally starts is you'll build a couple of rings and then you'll set it on the foundation, and then you just do ring by ring or plate by plate from there. On the Route 96 structure, we thought that there were going to be some pretty tight site constraints with getting underneath the existing bridges. So we initially planned to build a good length of the structure outside of the bridge and then pull it into place on the footing underneath. But as they started, they realized that they had enough room to get that done. So following through the pictures here, starting at the top left, this is at the beginning stages of assembly. These next two kind of show how it was fitting underneath the existing bridges as they went through. These two on the bottom, you kind of get an idea of what the grade looked like on that the unbalanced step L for the skews. The yellow you see here is an HDPE membrane that was placed around the structure to intercept de-icing salts to help with the service life of the structure. And that also minimizes the infiltration of water through bolt holes and seams in the structure that can, during the really cold winter months can sometimes become an issue. It's become a pretty common approach with these types of structures. You can use it either by wrapping the structure, or a lot of times it's just inserted within the backfill as sort of an umbrella that just basically intercepts surface water and makes it harder for it to get to the structure. Similar process for the County Road 1147 structure. This one was much easier to assemble. This was 5 plates per ring, so to save time, the contractor pre-assembled the 3 crown plates off to the side so that they could bring them in and basically bolt them on as a single plate. But this one had a lot more room to work with. Assembly went very fast. One feature with these types of bridge replacements is that you really don't have to get rid of any of the only bridge elements you get rid of when it's done is just the bridge itself. The superstructure can remain in place, or it can be removed. It's really up to what the owner wants. In most cases, it's by the time you take out the existing bridge, you've got the bridge piers buried quite a bit, so there's no harm in leaving them in there. I think of it as sort of a high strength backfill. So there, after the project was finished, I went to the contractor and to the engineer to get some feedback on kind of their thought process as they were considering options, and their final thoughts on how things went and where those benefits were. So I had mentioned before that the installed cost and time were, those were the main things that the contractor contributed. So in general, they figure they saved about 3 months on the project in terms of the construction speed, and about $500,000. At least that's what the contractor told me. That savings is, that's something I like to keep close to their vest. There were definitely some foundation cost savings. Both of these were on spread footings with more of a traditional bridge option. They would have been on deep foundations. And then there's always the reduction of long-term maintenance costs. In terms of structure selection from the engineer, they were looking at weight versus span capabilities, the room to construct beneath the existing bridges. This was really the easiest approach there. The similar things that the contractor had to say. There were some safety benefits as well, because there was never any head-to-head traffic during construction. A lot of times you would take all of the traffic from one of the bridges and move it on one lane in each direction on the other one as you're replacing those. In this case, they didn't really need to do that. So the main takeaway, some of the takeaways is in terms of economy. It's a lighter superstructure, lighter equipment to build, smaller foundations. From a construction standpoint, these are modular and simple. They're accelerated bridge construction structures. No specialty contractors were needed or used. A lot of county crews have been able to build these types of structures, earthwork contractors with a little bit of training. So wherever the assembler is at or the contractor is at, we can provide the training they need to get it And then finally, from a environmental resilience standpoint, steel is a recycled and a recyclable material. The plates used for this are generally minimum 90% recycled content and can be recycled into other bridges later. These are flexible structures. There's a high level of redundancy in the design, as well as the engineering backfill, that all significantly enhances the resilience. And that could be a subject for a future webinar topic, and I think. The reduced carbon footprint from the materials, fewer loads for shipping. These structures you can ship 50 foot of structure length or bridge width on a single truck in a lot of cases, and certainly lighter equipment for assembly. Those are all important factors, especially with some of the requirements with the new transportation bill talking about the environmental and the resilience requirements there. So thanks for tuning in, and I guess I'll just leave you with a deep thought there.
Thanks, Joe. Another great presentation. I am hoping the attendees are enjoying this as much as I am. I didn't know limiting all these people to only 14, 15-minute presentations were going to give us such nice, tight, interesting presentations, but that is great. Thank you, Joel. Joel, you do have a question from Fabio in the Q&A, if you would address that, please. And we're going to stay in Missouri. Joel mentioned, I think it was a 19 bridge bundled project, and we're going to stay in Missouri with Gary Wish, who is a fabricator and was involved with a bundled project that was very interesting in Missouri, how they did that. And so I'm very interested in hearing from Gary. Gary, I will stop him. You can share your screen and tell us about FARM.
Yeah, I'm trying to share now, Michael, and I don't know that it has come. Whoop, hang on.
You're coming up.
There
Hey,
yet?
that looks perfect.
All right, good. Well, as Michael said, my name is Gary Wish. I'm with DeLong's Incorporated. DeLong's is a steel bridge shop that's located in central Missouri. So we've worked for the Missouri DOT since long before I have been with the company, and I celebrated my 40-year anniversary last week. So I'm here to talk about what Missouri refers to as FARM. It's an acronym for Fixing Access to Rural Missouri, and it was a design build project that MoDOT came up with and took proposals about a year ago and made an award. Let's see if I can get it. There we go. MoDOT had several goals with this project. They had a minimum of 30 with an ultimate goal of 40 bridges that they wanted to have repaired or replaced across rural northern Missouri. Several of these had load restrictions, a 5 or 10 ton limit, and that kept school buses and farm equipment off of some of these bridges, and they wanted to get that taken care of. And due to the load restrictions, they made some of the bridges, they changed the lanes and striping and made them single lane structures, and they wanted to get all that back to where they had a minimum of 2 12-foot lanes on each structure. They had a budget of $26 million, and basically what they did for the contracting and consulting engineering industry, they said, we've got $26 million and tell us what you can do. So in real simple terms, they wanted to know how their criteria for determining the winning team was going to be: how many bridges can you repair or replace? How durable and long lasting will your bridges be? And because for many of the residents in these areas, and these are low traffic volume roads, but it's the only way into town. It's the only way into your school or your shopping district or whatever. So it was important to minimize the disruption to the traveling public. So Missouri came up with a scheme, and I know there's at least 1 or 2 MoDOT guys on the watching and listening. So gentlemen, I hope I don't mess this up. But they had a scheme where they awarded up to 100 points total. 40 points for getting the minimum requirement of 30 bridges built, some bonus points if you could get over 30 bridges, some points for quality and longevity. And then, as I had mentioned before, the disruption to the traffic was a big deal. So maintenance of traffic was important. 3 contractor engineer teams chose to bid on the job. Team 1 used all concrete structures. Team 2 used a mix of steel and concrete, and Team 3 used almost exclusively steel, and we'll get into a little bit more detail there. And they chose galvanized steel, and they, I don't know the details and how it all went down, but Team 3, who chose the galvanized steel, had the most points under bridge quality and longevity. So that certainly has to mean something. I show here a typical design plan that shows that the span lengths here are short, and this is typical of all the projects in all the bridges in this farm project. It shows as you can see across the top of your screen, a 31 foot, 45 foot, and 31 foot, and it calls it a continuous composite wide flange beam span. And these were actually designed simple for dead load and continuous for live load. And we'll get into a few more of those details here in just a minute. This is another page from the design plan, and my point here is to show the simplicity of the design. And this one is on about a 45-degree skew, but still just not very complicated at all. The details in the center show the shear stud spacing, so it is truly, in fact, a continuous for live load design. The detail in the lower left, which I'll try to blow up there a little bit, shows the channel diaphragm, and I'll have a picture or two from the job site. And once again, the engineer did a really nice job keeping this as simple as they possibly could. The lower right is a detail that shows the end condition at the intermediate piers. What they did here, and it worked out really well for us, they used an end plate instead of bearing stiffeners. So instead of 2 stiffeners, one on the near side and one on the far side, with a machine to bear finish on the bottom, they put an end plate on that can easily be done with a fillet weld. And then on the end of the end plate, at the bottom there, they've put in a 3-inch square bar that lengthwise for the bar in and out of the screen matches the width of the bottom flange. And we had not done anything like that going into this, but it's turned out to be a really simple and easy to fabricate design. This is page 1 of our shop drawing, and it almost exactly matches the design plan. We've added a few dimensions that were key to us. We've added some piece marks so the erector knows which piece to put where. We've added some general notes in the bottom left-hand corner and some typical clip and weld details, and we were ready to go. This is the first truck that's going out the door. It pulled out of our lot on I believe it was a Tuesday morning, about 10 o'clock in the morning. And that's the whole bridge. The entire bridge fit on one truck. This first structure was about 15 tons, and they range, it's one of the smaller ones, they range from in the low teens up to around 38 or 39 tons. So they won't all fit on a single truck, but this one did. And it pulled out about 10 in the morning, and I noticed it going out the door. So I called the contractor and I said, hey, I'd really like to come up and get some pictures of this being erected sometime in the next couple of days. Do you have a problem with that? And his response was, well, you better hurry up. And so I left my house about 6:30 the next morning, and it's about a 2-hour drive to the job site. And when I got up there, this is what I saw. On the right-hand side, you can see the crane that was just pulling off the pad that they had temporarily built in the creek there. So I got up to the job site less than 5 working hours or business hours after the truck had arrived on site, and I didn't get to see a single piece of steel being erected. All 12 of the wide flange beams, and all 12 of the channel diaphragms were already in place when I got there. So it was fast and easy for us to fabricate, fast and easy for the contractor to erect. I have a, excuse me, just a couple pictures with some details. The goal here is just to show the simplicity of the channel diaphragm. By the way, that's an embedded end at the abutment. So there is no end diaphragm. And if I remember right, and I'm sorry I don't have a picture of it, but I believe that instead of sitting on a bearing, the beam the galvanized rolled beam rested on a little piece of channel that was attached to the top of the piling, if I remember right. Here again, a blown up detail of the channel to beam stiffener connection. That channel was, at least in our shop, was hardly touched by anybody. It runs through an automated drill line. The program comes directly from our shop drawing, and so the holes were drilled and the saw cut it without with very little effort on our part. I show this to hopefully clarify the simple for dead and continuous for live design. You can see, and I hope you can see what my cursor's doing here. I'm trying to circle up where those 3-inch square edge blocks are, and those are welded to the end plate at the end of the stiffener, at the ends of the beams that bear on the intermediate piers, and that provides the load transfer across the compression flange. So and I don't know from the engineer standpoint how much weight they might have saved by going, instead of doing all simple span completely, by going to a simple for dead, continuous for live. But obviously with this design winning out, they had some success with the method. So I show this picture, and I know I'm running a little bit short on time, but I show this picture for two reasons, and one is to repeat that Missouri was interested. They wanted to keep these bridges as maintenance free as they could, so they were going to award points for long-lasting and durable structure. And you can see there that even the piling at the intermediate piers is galvanized, as well as the superstructure that we provided. So that was important to the DOT, and seemed to work out very well on this first bridge that was erected and the others that have come after it. And the other thing I wanted to show here is we all get caught up in, all of us in bridge design and construction and fabrication, we get all excited about major river crossings and major intersections, and that is a big deal. But I tell you, for the people who travel over these bridges, even though these traffic counts are in the several hundred per day, to these people, to get to and from town, to get to and from their children's school, these are every bit as important as the major river crossings. And this, I'm on the east end of the bridge facing west as I take this picture, and you can't see any structures or anything else going on for about a half mile going up that hill. And if I turn around and look to the east, I have exactly the same thing going on. So they're out in the middle of nowhere, and they're easily forgotten, but they're very important to the residents in the area and the state that owns them. So that's all I have. Michael, I'll turn it back to you. Hopefully I'm a minute or two ahead of time, and we'll answer any questions if we got them.
You are. Well, that's a great project. A design build project with some true metrics that helps the owner decide on what type of bridges to build. And of course, we are pleased that they chose steel bridges, since this is a steel bridge webinar series. So thank you, Gary. Excellent presentation. And with that, I believe that the questions have been, well, they've been thoughtful, they've been presented in the Q&A, they've been answered. And so I thank you for the panelists that paid attention to those. Of course, today is Monday, or I'm sorry, Wednesday, Monday, June 6th, sorry, Steel Bridge case studies. And I have thoroughly enjoyed this. Thank you, Mark, Jeff, Joel and Gary. And Dan Snyder has been putting in the chat box links to more information on these particular projects or contacts for our presenters today. If you have more questions or you are interested in some of these bridge projects. And with that, we'll close out because I don't think we have any questions that we need to deal with this slide that says, you know, we really encourage you to visit the shortspansteelbridges.org website where you can find information on so many things. Certainly you can subscribe to the weekly newsletter, which Dan does a very good job at on every Friday. You can find some of these suppliers that can fabricate or manufacture and deliver you a bridge. Next, or on Wednesday, we're going to look at this E-span 140 to where you can get a preliminary design for a short span steel bridge in just a matter of a few minutes. And Professor Greg Michelson is going to be presenting that. On Wednesday, you're also going to see a very versatile true design software package called LRFD Simon from the National Steel Bridge Alliance. And then if you are interested in getting more information to your region or to your company or to your counties, the Short Span Alliance has standard webinar or standard workshops that we are willing to come visit your region, and there's no cost to you. The Alliance ships everybody down there and produces those workshops for you. So if you're interested in that, you can contact the Alliance through the website. And with that, Dan Snyder, I think we are done, aren't we?
We are done. I do not see any other questions in Q&A or chat. So
yes, you guys are getting, you guys are, the attendees are doing very good job at submitting their questions through Q&A, and our panelists are doing an excellent job of answering those on the fly. So with that, I'm going to shut down today's webinar, and we look forward to seeing you on Wednesday. And don't forget, get into those modules in Canvas, complete those quizzes so that you're working towards that certificate. Thank you, everybody. We will see you on Wednesday.